Okay, today we are doing a day on graphing, and basically something we would have taken a week to teach you last year. We are going to do in about 25 minutes. All right, first up, do you remember if you had a graph that was going to shift, you'd start by saying, like, let's say x squared, but then if you put like a +3 in there and a -7 out there, it moves it around. Does that ring a bell? The +3 moved it which way? Left. And then how about the -7? Down. All right, good. What if I throw in a 5 out front? A stretch. Now, it's important to say which kind of stretch, and so I want you to get used to saying vertical and horizontal, because on the inside is horizontal. It's horizontal on the inside and vertical on the outside, like just like the dwarves, hi-ho, hi-ho. This is hi-vo. Horizontal on inside, vertical on outside. All right? So then, when you see the negative, like right here, that's a vertical reflection. It's a lot safer than saying a reflection over the x or y axis, because people get confused all the time, and it makes sense. If that's a vertical reflection, it's a reflection this way, right? Do you get how that looks exactly like the y axis? So people get that confused and they think, oh, it's a reflection over the y. No, that's actually going over this axis, which is the x axis. So I'd prefer you not to try to guess whether it was x or y. Granted, you can draw it out and go, okay, I'm going over that axis. That's the x-axis, so this is a reflection over the x-axis. If you just know it's on the outside, it's going to automatically be vertical. So that's a vertical reflection and a, what's that 5 again? What kind of stretch? A vertical stretch. Okay, good. And on the outside, this is a vertical move, but it's easier to just say down, because there is no such thing as a horizontal down. You can just say down. All right, down 7. And that's 3 to the left. All right, if you really remember that, would you please try to write out what all 4 of these things would do to our function? That's 2 of them. That's the 3rd. That's the 4th. What would these 4 things do to the function? I'll pause for a second while you try that. You should have said that this was a vertical reflect. If you said flip, you got to get used to, you're in pre-calc now, you have to use the right terminology. That's a vertical reflection. This is a vertical stretch. That is it is horizontal, but there is no right vertical. So if you say right 5, and then you say up 10, you've got it. Raise your hand if you had those right. Okay, good. So that's important for today, but more important is once you actually have the thing on the graph, the question is, does this have certain kinds of symmetry? All right, that's one of the main things. And this had a certain kind of symmetry. Remember, there's x-axis symmetry, there's y-axis symmetry. Which one was this? Y-axis symmetry, because across the y-axis is where you got the symmetry. Okay. Now, it's my goal to make your life challenging and complicated, so we have a new name for that. This is not just called y-axis symmetry. It makes the function an even function. So we call it even symmetry. You remember how it was like y equals x squared? Now, does that mean anything that has a squared in it has automatically got even symmetry? No. As soon as you add like 3x to it or something, then it won't necessarily have even symmetry. But I don't want you to think of like, oh, the number's even or the number's odd, so therefore I can tell. But it is kind of a tell that it's maybe going to be even if it's got a squared on it. And conversely, odd symmetry is things like y equals x to the 3rd. And we saw that before, but we didn't call it odd symmetry. We called it a reflection across. Do you remember this? The origin. It was origin symmetry, yep. That kind is odd. And there was one other kind of symmetry that we even taught you. it was the kind of symmetry where if you had something that went like this, then it would reflect down here and go like that. And that was symmetry across the x-axis, and that's not odd and it's not even. So there's only two you have to worry about now. It's either got odd symmetry or even symmetry. So I'm going to draw you some pictures just to make sure this sets well in your brain. Odd, even, or neither. Now, assuming that I'm off a smidge here, like that should be going through the origin, for example, okay? That would be odd symmetry. All right, that was a pretty bad drawing, but how about odd or even? Odd. It's got origin symmetry. Again, drawing may not be perfect, but all right. So odd, even, or neither. Even symmetry. Okay. Either. Okay, good. Now, how do we tell algebraically if something's got odd or even symmetry? If you have, here's a proof thing. You remember those proofs where we proved f of g of x was equal to g of f of x was equal to x, and you drew the line and you solved this side and it came out to x, solved that side, came out to x. Then it was not symmetry, it was inverses. Those are inverses if they did that. We've got something like that now. It's a three-part chart. I think this is the easiest way to teach it. I actually used to teach it a different way, and somebody showed me this, and I was like, man, that's really easy. I think I'm going to do it that way. You start with f of x, just f of x. And then you do f of negative x. And then you do negative of f of x. I'll show you what that means. So let's say that I have a function of y equals x squared. And you know already that that has what kind of symmetry? Even symmetry. So that would be our f of x. That is our standard function that we'll start with here. Notice y is f of x. So, okay. So f of x equals x squared. Well, f of x is, of course, x squared. And then you can write the same function again, except without the x, and again, except without the x. Because we're going to replace the x. In this case, we're going to replace the x with what? Negative x. And in this case, ooh, what should I do? Negative on the outside of the function. Now, which of these are equal? We got to simplify them down now. This one's still x squared. This one, when we simplify it down, it becomes what? X squared. How about that one when we simplify it down? Negative x squared. Okay. Now, here's the way you can tell what's what. If these two are the same, then you have even symmetry. If these two are the same, you have odd symmetry. And I know it's going to be hard to remember, like what order to put these in and stuff, but f of x being first is the same thing we did last time. And then putting the negative on the inside, I guess you'll just have to remember that you start with the inside, and generally on hard math problems you start on the inside. So, and then this one's the negative's on the outside. And the one of the things that I remember is that these both have negatives. Huh, that's odd. Remember it any way you want to, but that's all way you could remember it. Yes? I know what you're saying. If it's like this, what if these two are the same? That means absolutely nothing. Because we only have two choices. It's either odd or it's even. And anything other than that means what? If it's not odd and it's not even, it's neither. So that would be a neither, but then again, so is not equaling anything. Like you get totally different things for all three of them. That would mean a neither. So I don't want you to think that these outside ones being equal means anything. It really doesn't. It just means it's not even and it's not odd. Therefore, we can default to neither. Yes, ma'am. It's a good question. They will never all three be the same, or you did something wrong. Because if they were all three the same, then it's odd and even at the same time, which it can't be. Unless you think you can draw me an example of something that has even symmetry and odd symmetry at the same exact time, I don't think you can. So if they were all equal, I would be like, crap, I screwed one of them up. I got to go back and figure that out. All right, so I'm going to have you try one of those. Everybody start with a clean spot in your virtual paper. And let's say that the function is this, x squared plus 2x. Y is the same as f of x, right? So I'm going to say f of x equals that. And I'd like you to try making that three-part chart. See which of them are odd, or sorry, whether this is odd or even or neither. Yes? Good question, but it is not a function. Otherwise, I think you got a point there. A circle would have even symmetry, and it would have odd symmetry. It's only thing I can catch you on that one is the circles are not functions. Another one that I thought of when I was trying to think through like all the possibilities is that guy. Remember the 1 over x function? It's kind of weird. It's got odd symmetry, also known as origin symmetry. An origin and odd both start with O's, which is a good thing. But it does not have even symmetry. To have even symmetry, it'd have to be something over there. And as soon as I draw that one in there, now it's not a function anymore because it won't pass the vertical line test. So I'm pretty sure nobody's going to find me a odd and even function. F of x is the first thing we start with. But are you saying would f of x equals 0 be a function? I'll put it this way. I can't, it has not been reflected across either axis, but then again, you can't like prove that it's good. It's an interesting point. I don't know, because I know it doesn't. How about this? We'll test it using the system right after we're done with the problem that we just did. You've got an interesting point there. We'll see if it passes or fails the system. So here's the system. F of negative x is next, and then negative f of x is last. And if these two are the same, it's what? Even. These two are the same, it's what? Odd. Okay, good. So this is x squared plus 2x. This, I like to write it again without the x's. And then I'll be dropping in a negative x. And this last one is negative of the whole function. The whole function is x squared plus 2x. Notice that parentheses there, most commonly screwed up place on the whole chart, because people forget that they are going to have to distribute this negative, and they will just slap a negative at the front of it without the parentheses and forget to distribute the negative. Okay, back to this. Are these really equal? We'll find out. Square that, you become x squared. Simplify that, becomes minus 2x. Is that really equal? No, and therefore it's not even. I've checked. Now I'm going to check these two. Negative x squared minus 2x. Are these equal to each other? No, so therefore it was not odd. And if it's not even and it's not odd, it was a neither function. All right. So that's proving, not inverses. This is proving whether functions are odd or even. Because you can look at the picture, and that is an okay method to go, okay, I can tell by looking at that since it has symmetry across there, that is an even function. You can tell by inspection. But if you don't know what the function is, then like you don't know what the equation is, you can't prove it any other way. So here's that other one that somebody said, what about f of x equals 0? Let me stick that in for my f of x, f of negative x, and negative f of x. Well, f of x is 0. F of negative x is 0, right? Because I put in a negative anything, I'd still have 0. And then negative of f of x is negative 0, which is 0. So we're never supposed to have this, like that's never supposed to happen. So therefore, this is not even or odd symmetry, but I can't explain what it is. Here's the thing. If you don't have any reflection, like there's nothing reflecting across here, you don't have symmetry. And I think the thing is you can't reflect something that's on the mirror. You know what I mean? You can't reflect that anywhere. It can't go anywhere. It can't go up, down, left, right. It stays where it is. So it's kind of a not answer, but that's the closest thing I've ever heard. So good idea. Okay, so the next topic is this slide. Everybody get to this slide. Increasing and decreasing. If we read from left to right, would you agree this sometimes increases? And then sometimes it kind of holds its own, stays the same. This is supposed to be straight across here. Okay, so if it holds its own like that, that's called constant. And then when it goes down again, that's called what? Decreasing. But how do we describe where it was increasing? Well, at the beginning. Well, you have to be specific in math. From here to there. Notice those are x values. So it was increasing from -6 until we hit 1. You could probably have a good argument about whether you use brackets or parentheses, because brackets implies that it increases at -6. But is it really increasing when you've hit the very last point and it's not going to go up anymore? I don't know. It's an argument that you could have. It's like saying the last step on the ladder. You reach the last step on the ladder. Is it still increasing there? How high you're going? Well, anyway, most people use parentheses. So decreasing. Well, it's decreasing from basically here to here. I'm going to say that that's from 1 to 4. Again, the line's really thick, so it's hard to tell, but let's go with from 1 to 4. It was decreasing. Oh, constant. Sorry. I moved that down to constant. Good catch. And then decreasing from 4 to, what if, I think the reason they went way off the graph is to kind of imply it's going to keep going down. So from 4 to infinity. Now, you have every right to know whether there's an arrow or not, because if there's an arrow, the answer is different than if there's not. Okay, so in this case, I would have said, yeah, there's an arrow. There's supposed to be an arrow, and therefore it's to infinity. Because if it actually stops, like let's say I erase just a little bit of this line, and I don't go off the graph, and I go right there, then my answers are different. Now, if it was going down forever, then I'd have different answers than if I just have it stop right here. So you have every right to know whether or not it's supposed to have an arrow on the end of it or not. All right, so now let's go. Here's another key point. These are x values, not points. You get how that's not the point, -6, 1. It's a totally different thing. These are both x values. So if I had a graph that looked like this, and I said, here's -3, 2, and here's 8, 7, the question would be, where is it increasing? The x values, from -3 to 8. I get its height went from 2 to 7, but that's not the question. The question is over what interval from here to here it was increasing, and that's the x values. All right, so these are all x values for increasing or decreasing. Next thing is local maximums and minimums. Would you agree that that is a high spot and this is a low spot? And they're therefore maximums and minimums. It's that simple. Local maximums are in the local area, around this area, it is a high spot. And around this area, it's a low spot. So those are called local mins and maxes. This one is an absolute max because it's the highest the graph ever went. Absolute max just doesn't mean it's a locally a maximum, it's also absolute a maximum. Now this is important. Can you be both? So let me ask you this question. Could you be both locally the strongest kid in our high school and the strongest kid in the world? You could be both, and therefore you can give both labels. So if I ask what are the local maximums, some kids don't list this one because they're like, well, it's not a local maximum, it's the absolute maximum. No, it's both at the same time. Okay, so this is a local max, this is a local max, and only this one is the absolute max. How about this one? It's the local min for sure. Is it also, considering I put dots on the end and not arrows, is it also the absolute min? Yes, it's the lowest it ever went. But as soon as I let one of these things run and go down and have an arrow on the end of it, then do you get, it doesn't, you don't say that the absolute min is infinity. This is an important point. Because infinity is a concept, it's not a place. You can never reach infinity. So you say it has no minimum then. If it goes forever downwards, this is not a minimum of negative infinity. It's there is no minimum. Because if I said, for instance, Apple stock, I'm sure it's going up today. You know why? Because Galaxy Note 7s just got, they were starting on fire. You heard about that probably, right? Maybe you don't have any friends that have these things, but the Galaxy Note 7 is the flagship product from Samsung. And they had fires where the phone would just like spontaneously, some of them, they said, weren't even connected to a power source, but I think most of the time it was connected to a power source. When it got connected to the power source, it could overheat and like start on fire. And they had an instance of some little kid that was holding one when it burst into flames. I mean, it got really scary. So they recalled them and started replacing them with different phones. But then those started to burn also. So the company just last night, like during the middle of our night, during the day in Samsung land, decided to stop selling them. Like, so that's the main competitor for the iPhone. Just stopped selling it.
They also released a press release that turn off your Galaxy Note 7s, don't turn them on.
Yes, they basically, they're trying, I'm sure, to cover their butts. Like, don't use that phone you bought from us. So it's a bad day for Samsung, no doubt. And that means probably a good day for Apple. So Apple stock is going up. Let's say it keeps going up. Would we say that it has no maximum? Yeah. Would we say its maximum is infinity? No, because you can't get to infinity. Okay, but it has no maximum. Like it'll go up, and we don't know where it'll stop. All right, and I don't know that for sure. I haven't even looked at Apple stock, but I'm assuming.
Currently trending down, but over the past 5 days, it's gone up quite a bit.
Really, Apple stock went down.
In the past hour and a half.
In the past, okay, today though, like for the day, it's down. Wow. Yeah, I know it's up. It's up overall, but just I expected today for it to jump up a lot when their major competitor. It's kind of like Ford and I don't know Chrysler. That isn't even a real company anymore, is it? I don't know, Ford and Toyota. They're two major competitors, right? And then one of them, they can't sell their cars anymore. You'd think the other one would be like, whoa, we're going to make lots of money. But Apple stock didn't go up. You just never know. All right, so anyway, the reason I picked that is because they're things that go up and down, like stock prices. You know, they can go up one day and down the next day, and up one day and down the next day. And this would be a what? Local minimum. How about this one? Local max. How about this one? Absolute max. And local max. And what if I put a thing like this? Is this still a local minimum? Is it an absolute minimum? No. It is a local minimum, but not an absolute minimum. And let's say this was at the point, let's say it's in Apple stock where it reached its low back when people were afraid that Apple wasn't going to, I mean, nobody really knows why stocks at their lowest point, but there was some concern that Apple's new phone wasn't going to be well received, like the iPhone 7. For a while, right after it got released, a lot of people were like, oh, there's nothing different about it, but actually they're selling a ton of them. So they thought it was a bad news thing, so the stock reached its local minimum that day, and let's say it was on September 10th or something like that, right after they announced the new phones. It went down a fair amount because people thought, oh, nothing new. We were expecting a big new cool phone. And let's say its price at that point was $106 or something like that. Can't remember exactly what it was, but something like that. Then, since then, it's gone up, because people, they started getting reports of how many phones were being sold, and there was tons of phones being sold. Like Sprint sold, I don't know, it was 5 times as many phones as they did last time that they had an Apple phone come out. And so they were like, I guess this thing's kind of popular. So I asked a friend who just got one, and he went from a 5 to a 7, and for him that was a massive jump from a 5 to a 7. So he loves it. He thinks it's amazing. And I know if you ever jumped in a pool by accident, you'd be really happy you had it because it's water resistant. They've taken them down. How deep did you say before? 35 feet or something like something. Maybe it wasn't you. Somebody had said they did like some guy took it down 35 feet and it still didn't let water in, but they won't guarantee that because the deeper you go is more pressure on the thing. So, sir. Yes. So this is a local maximum, and this is a local maximum, and you could have 35 local maximums as long as in their area they're the highest place. So like you could have, that's a max, that's a max, that's a max, that's a max, because in their area, like think of it as little neighborhoods. Somebody lives on top of that, they're living in the highest spot in the neighborhood. Highest spot in the neighborhood. These people are living in a valley, but they're not, it's not the deepest valley, but it's still a local minimum. And this was a local maximum. So there can be many, many local mins and maxes. All right, these are all good questions. Let's get to, go ahead, the actual assignment for today, which starts here. First, you have to graph it. I'll give you a hint. Write this backwards and it'll graph easier. Y equals negative x plus 2. Why did I do that? Because now it's in what form? What form? Slope intercept form. Very good. And the slope is negative 1 and the y-intercept is 2. So then you can go, oh, so we start here and the slope's negative 1. I can do that. Now, for some of these, you're going to have a harder time graphing them than that. Some of these, you may want to make an XY chart. I have said this a zillion times. I'm going to say it again. The XY chart is your best friend on every graphing problem that we do. Because when they get complicated, which they will, you'll need the XY chart to figure out where the graph is. And if I wanted to on this one, I could stick in x is 0, and then I go 2 minus 0 is 2. 0, 2 is on my graph. And you just make a whole bunch of points and connect them. You can always do that. This thing is so powerful. It'll even work when your graphs are things you don't even understand. Sine of 2x is equal to y. You can still take a calculator and figure out what sine of, stick in any number you want. Stick in a 1, for instance, and it'll be sine of 2, which is actually 0, undefined. And you could stick in something like 1/2, and that'd be sine of 2 times a half. Anyway, my point is you can use it on even really complicated equations. So the XY chart, I expect to see tons of those when they get complicated. Now, like this one, I know it's a parabola shifted up 1. So I can do that in my head. Over 2 up 4, 1 over 1, over 2 up 4, and there. I did that without any XY chart. But when they get complicated, you'll need one. All right. Now, I can look at that and say it's even. But they said test for symmetry. And I want you to get used to these. We'll start with just doing a few of these where I actually want the whole chart. Number 3 is one of them. I want you to not only say I think it's even, I want you to prove it with this. F of x, f of negative x, and negative f of x. So f of x was x squared plus 1. F of negative x, you're going to stick that in here. And negative of the function goes like that. You simplify them all down. If these two are equal, then it was even, which is what I think it is. But you can prove it by using that little system. And I want you to make a chart for number 3. I also want you to prove number 8 and number 12 with the little chart thing. Question? 8 and 12 on this page, and then the other one, number 3. I don't need you to prove number 1. That's too simple. But so all I'm asking you to do is 3 of those charts for 3 and 8 and 12. All right. Then you may skip problem 18, but I think you should do one piecewise function. We do a decent job of reminding you about things that we've taught you before. This would be good for you to go back and do another piecewise function. I'll remind you, I like to put a dotted line on the borderline because the borderline is super important. And this side might look something like this. On the other side might look something like this. And you're going to have to figure out what the functions look like. XY chart's your best friend. Make an XY chart if you're like, I don't remember what that looks like. Then go make XY, stick in anything you want for X, find some points. But make sure your X's are less than 0 because that'll make a graph over here. Okay. This is the most important page because it sums up, there's only one of each. Do you know what a y-intercept is? Well, I can look over here and find the y-intercept like that. How do I write that? As a point. That is the point 0, comma, -1. So make sure you write your points as points. But your intervals are x values. So where is it decreasing? For instance, it's decreasing from there to there. It's the x value of this to the x value of that. The x value of this is 0. So it's something to 0. I'll let you finish that off. Don't forget about domains. Notice these have dots on the end, not arrows. So they don't go forever. They just, that is the lowest it goes for this whole function, which says something about it. Okay. That's all you got for today.